Hi there, I'm Shyan, and I'm here to tell you a bit about work done by Ryan Williams and myself on determining the complexity of this fascinating problem called majority 3-SAT. But before, okay, we're gonna try recording again. Hi there, I'm Shyan, and I'm here to tell you a bit about work done by Ryan Williams and myself on determining the complexity of this fascinating problem called majority 3-SAT. But before saying anything about majority 3-SAT, I'm going to recall some definitions surrounding this problem's more popular cousins, SAT and sharp SAT. So the first half of this video might be a review of some basic concepts, but will hopefully help set the context for what this majority 3-SAT problem is all about. Let's begin with the satisfiability or SAT problem. In SAT, we're given as input a Boolean formula in conjunctive normal form, that is a CNF formula. This is just some formula phi on n variables x1 through xn, which can be written as the conjunction of several clauses, where each clause is the disjunction of some variables and their negations. We'll call these variables and their negations literals and write them using these else by symbols. In this video, we'll represent formulas using this flattened out form on the right, where we simply list out each of the clauses in the formula. Each clause is a constraint which says that at least one of its literals must be set to true, and the overall formula phi is mandating that all these constraints get satisfied. So the SAT problem takes as inputs such a CNF formula and asks if that formula is satisfiable. Does there exist an assignment of true and false to each variable such that phi evaluates to true? All its constraints are satisfied. An equivalent way to pose this question is to ask if phi is true with positive probability, given a uniform random assignment to its variables. This PR phi, probability of phi notation, just denotes the total number of assignments which satisfy phi divided by 2 to the n, the total number of possible assignments to the variables of phi. In other words, it's a count of satisfying assignments normalized to be some fraction between 0 and 1. Perhaps the most important result about SAT, the reason it occupies such a central position in complexity theory, is that by the Cook-Levin theorem, SAT is complete for the class NP. If we ever want to show a problem is NP complete, we can prove this just by reducing SAT to it. A natural sparse version of SAT is the 3-SAT problem. It's the same task, but now the input is not a general CNF formula, but instead a 3-CNF. That is, a formula where every clause has width at most 3. In general, given a positive integer k, a KCNF is a formula where every clause has at most k literals. Even though 3-SAT is a restricted form of SAT, it also remains NP complete. This is because we can reduce SAT to 3-SAT just by taking any clause with width greater than 3, introducing some new helper variables, and then splitting up the original clause with these helpers into smaller clauses with 3 variables each. This sort of transformation turns out to preserve satisfiability of formulas. So SAT is NP complete, and its sparse version 3-SAT is also NP complete, and this is useful for certain reductions. Something similar happens in the world of counting. In the sharp SAT problem, we're given a CNF formula phi and are tasked with computing its exact fraction of satisfying assignments. Since we know the number of variables n in the input formula, this is equivalent to counting the number of satisfying assignments. Just like how SAT is NP complete, sharp SAT is complete for the class sharp P, which is the complexity class associated with counting problems. I won't say much about this class except that by results like Toda's theorem, we can think of sharp P complete problems as being in some sense even harder than NP complete problems. As before, we can consider a sparse version, sharp 3-SAT, where we're given a 3-CNF and want to compute its fraction of satisfying assignments. If we modify the reduction from earlier, then it turns out that given any CNF, it's possible to produce a 3-CNF with the same number of satisfying assignments, even though the new formula might have many more variables. And because of this, sharp 3-SAT is also sharp P complete. And with smaller polynomial interpolation-based arguments, we can even show that sharp 2-SAT is sharp P complete. All right, now that we've defined the SAT and sharp SAT problems, we can introduce the majority SAT problem. In this problem, we're given a CNF formula phi and want to know if it's satisfied by at least half of all possible assignments to its variables. If we consider the fraction of satisfying assignments as some number between 0 and 1 written in binary, majority SAT is asking us to compute this fraction's most significant binary bit. And this problem is complete for the class probabilistic polynomial time, which I won't formally define, but you should think of as about as hard as sharp P. All right, now finally, with all that set up, we can introduce a main protagonist of our work, the sparse version of majority SAT, majority 3-SAT, which asks, given a 3-CNF phi, is its fraction of satisfying assignments at least 1/2? So far, we've seen that SAT is complete for NP and remains NP complete even when we restrict to 3-CNFs. And sharp SAT is complete for the class sharp P and remains that way even when we restrict to 2-CNFs. So what happens with majority SAT? Well, by analogy with these previous results, it seems like majority 3-SAT should perhaps still be complete for probabilistic polynomial time. But at least for the past several decades, no one knew the complexity of majority 3-SAT or even the complexity of majority k-SAT for any fixed positive integer k. The main trouble to showing that majority 3-SAT is hard seems to be that standard tricks of reducing clause width don't really work here because they introduce several new variables. And once you add new variables, the fraction of satisfying assignments drops a lot. Remember, this fraction is the total number of satisfying assignments divided by 2 to the n, where n is the number of variables in the formula. So if you increase the number of variables, that is, increase the value of n, that forces this fraction to become very small. Because of this, it's not so clear how you could get a reduction from majority SAT, this PP complete problem, to something like majority 3-SAT. So we have this mystery where, unlike in the cases of SAT and sharp SAT, where the complexity for KCNFs has been well understood for a long time, the complexity of majority KSAT has been open for quite a while. This problem is already interesting in its own right because it's a very natural question to ask and is closely tied to these other satisfiability problems, which are all canonical hard problems for their respective complexity classes. Understanding the complexity of majority KSAT is also interesting because of connections to certain planning and scheduling problems in AI. There are a wide variety of inference tasks in this area where the main theoretical evidence of hardness for such problems comes via reductions from majority SAT. And if you're interested in showing that bounded degree versions of these inference tasks are also hard, then it would be natural to try and show that majority 3-SAT is PP complete and reduce from that. Because of this and related considerations, over the years, many researchers have raised this question of whether majority 3-SAT is a hard problem. And typically these papers note that it's not known if majority 3-SAT is complete for probabilistic polynomial time. And so in their applications, they end up needing to search for other problems to reduce from. In any case, this all motivates the question, what is the true complexity of majority 3-SAT? And that is the main question our work answers. Well, because the title of this video already spoils that answer, I won't delay any longer, but it turns out that unlike in the case of SAT or sharp SAT, the majority SAT problem becomes significantly easier when restricted to formulas of small clause width. In particular, majority 3-SAT can be solved in polynomial time. More generally, instead of considering 3CNFs, we could consider formulas whose clause width is at most k for some fixed integer k. And instead of checking if the fraction of satisfying assignments is at least 1/2, we could try and determine if this fraction is at least some fixed threshold rho. This more general problem can also be solved in polynomial time, provided rho is some positive rational with constant denominator. So these are the main theorems from our work, and with the short time we have in this video, we won't see the proofs of either. However, we will go through the details of proving a simpler result by presenting an algorithm which solves the majority 2-SAT in linear time, and this will showcase some key ideas used in the proofs of our theorems. After that, we'll give brief comments about how those ideas generalize to solve majority 3-SAT. Before going into the majority 2-SAT algorithm, I'll give one bit of intuition for why majority k-SAT should be easy, even though majority SAT in general seems so intractable. And the intuition is that while in general CNFs, we can have very satisfiable formulas, in KCNFs, observing even a single clause already drops the fraction of satisfying assignments down a lot. For example, a clause of width 3 is satisfied by only 7 out of 8 assignments to its variables. This means that for 3CNFs, testing if the fraction of satisfying assignments is at least 7/8 is trivial, because you can just check if it has at least 2 distinct clauses. So this might already be a hint that testing if the fraction is at least 1/2 should also be easy. With that intuition set, let's begin trying to solve majority 2-SAT. We're given some 2CNF phi and want to know if its fraction of satisfying assignments is at least 1/2. Imagine, for example, the first few clauses of phi look like this. Because each clause involves at most 2 variables, the fraction of assignments which can satisfy a given clause is already a constant less than 1. For example, if we consider this first clause, only 3 out of 4 assignments to the variables x1 and x2 satisfy it. So this already implies that the fraction of satisfying assignments of the overall formula is at most 3/4. Next, suppose we find some other clause that shares no variables with the first one, for example, the third clause in this list. Then this clause is an independent constraint from the first. In particular, regardless of the assignment to the variables x1 and x2 in the first clause, the second clause is satisfied by 3 out of 4 possible assignments to its variables. Because of this independence, viewing these two clauses together shows that the formula is satisfied by at most a 3/4 squared fraction of the time. This reasoning shows that if we can find enough of these disjoint clauses, then the fraction of satisfying assignments must be very small, and we can just say the answer to the majority 2-SAT problem for this formula is no. So this motivates the idea of searching for clauses over disjoint sets of variables as a way to solve this problem. And here's a very natural way to look for such disjoint sets. Imagine we're given some 2CNF We're simply going to scan through its clauses in a greedy fashion. We start by taking the first clause and including it in our disjoint set. Then we go to the next clause. If it shares any variables with the clauses we've already picked, we skip it and move on, but otherwise we add it to this disjoint set we're building up. We keep doing this, extending the disjoint set by adding clauses which share no variables with previously added clauses. At the end of this process, we've scanned through the entire 2CNF and we'll have found some maximal set of disjoint clauses in the formula in linear time. After this search, one of two things could happen. First, it could be that we find a large disjoint set. And by large, I just mean a disjoint set with at least 3 clauses. Because if we find 3 independent constraints in the 2CNF, each of these clauses is satisfied with probability at most 3/4. So the total fraction of satisfying assignments of phi will necessarily be at most 3/4 cubed, which is less than 1/2. So in this case, we already know our formula is a no instance for the majority 2-SAT problem. So that's great. The other possibility is that we run this greedy algorithm and only find a small number of clauses to include in this disjoint set. For concreteness, imagine we only found 2 disjoint clauses. Because of how the algorithm works, we know that if we included these clauses in the disjoint set but no others, every other clause in the formula must actually share some variable with the clauses in the disjoint set. So this formula we're looking at has a very rigid structure where a small set of variables hits all the clauses. Let's call this hitting set of variables H. We'll try and use this set to reduce our formula somehow. Consider an assignment alpha, which sets each variable in H to true or false, indicated by 1 and 0 respectively. Because every clause of phi contains a variable from H, if we assign the values dictated by alpha to the variables in phi, we get some new induced formula, which is a 1CNF. For example, suppose we had an assignment like this, where x5 is set true and the rest of the variables in H are set false. Then some clauses will already be satisfied by this partial assignment, and some other literals will be false and not satisfy their clauses. And when we remove all satisfied clauses and unsatisfied literals, we're left with a new 1CNF, whose satisfying assignments are precisely the satisfying assignments of the original formula, which extend the partial assignment alpha we're considering. Intuitively, this shows if our formula has a small disjoint set, our 2CNF is very close to some 1CNFs. And this is useful because counting satisfying assignments for 1CNFs is easy. If we have a 1CNF to satisfy it, we just need to simultaneously satisfy a list of unary constraints. And either these constraints are inconsistent, that is, we need to satisfy both a variable and its negation, and we can say the formula is unsatisfiable, or the constraints have literals coming from different variables. And in this case, the fraction of satisfying assignments is going to be equal to some power of 2 we can compute given by this formula on the screen. And this holds just because if we take a uniform random assignment to the variables, each constraint will be satisfied independently with probability 1/2, and there are v distinct constraints. Returning to where we were in this majority 2-SAT problem, we were considering what happens if we find a small disjoint set in the 2CNF. In this case, we saw that we actually get a small hitting set of variables, and each assignment alpha to these variables induces some 1CNF phi sub alpha. So to count satisfying assignments for phi, we can loop over these alpha assignments, add up the counts for each phi sub alpha, and get the total count. So overall, we take the hitting set H, we try out all assignments alpha to the variables in the hitting set. Each assignment induces some formula phi sub alpha, and each phi sub alpha is a 1CNF, so we can compute its count of satisfying assignments. So by our equation, we can count satisfying assignments for the original 2CNF as well. And if this true fraction of satisfying assignments is at least 1/2, we return yes, and if it's instead less than 1/2, we return no. That concludes the argument for the majority 2-SAT algorithm, which I'm going to quickly summarize now. To solve majority 2-SAT, we scanned through the input formula phi and looked for a maximal set of clauses on disjoint variables. If the disjoint set we found had more than 3 clauses, then the formula is very unsatisfiable and we return no. Otherwise, the disjoint set has fewer than 3 clauses, and by maximality, the variables appearing in these clauses form a hitting set for the formula. We can then loop over all assignments to the hitting set, get a 1CNF induced from each assignment, count satisfying assignments for those 1CNFs, and add everything up to get the total count of satisfying assignments of phi and use that to solve the problem. The main idea of this algorithm was that we can solve majority 2-SAT by looking for clauses on disjoint sets of variables. If we find a large disjoint set, we have identified some sort of bad subformula, which is a witness for the fact that the fraction of satisfying assignments is less than 1/2. Otherwise, if we find a small maximal disjoint set instead of a large one, this implies that 2CNF is very structured, and we can compute its fraction of satisfying assignments exactly by decomposing into a direct sum of 1CNFs. Then we return yes or no according to the value we compute there. This is a basic example of a structure versus pseudo-randomness dichotomy that pops up a lot in combinatorics, specialized here for 2CNFs. And this sort of split between bad subformulas and structure also holds for 3CNFs, but in a more complicated way. If we use the ideas from our majority 2-SAT algorithm directly to try and solve majority 3-SAT, we recover some similar cases. If we find a large disjoint set, we still return no. And if the input is nicely structured, we may be able to decompose it as a direct sum of 1CNFs. But these are not the only cases that might occur, and to handle these complications, it turns out it's not enough to only examine disjoint sets. To solve majority 3-SAT, we end up searching for an additional structure known as a sunflower. And with this extra structure, it turns out just like in the case of majority 2-SAT, we get a split between bad subformulas and structured inputs, and we can solve the problem in either case. In this video, we won't actually define what this interesting structure called a sunflower is. All we'll say is that a sunflower is some sort of special subformula where clauses overlap on a few literals in a controlled way. And that's all we're going to say about solving majority 3-SAT in this video. To summarize, in this video, we saw an algorithm for majority 2-SAT. It worked by arguing that either a 2CNF is very structured, so we can easily count satisfying assignments, or the 2CNF is random-like and quite unsatisfiable. The way we identified the structure was by searching for disjoint sets. We noted that we can also solve majority 3-SAT in an analogous fashion that ends up exploiting a more complicated sort of characterization of the input formulas. Either a 3CNF is very structured, or it has some bad subformula, which makes it quite unsatisfiable. And we identify this more involved structure by searching for something called a sunflower, which we didn't define in this talk, but you can learn about in our paper or in the literature surrounding CNFs and set systems. In general, we can check if a KCNF has at least a row fraction of satisfying assignments whenever rho is a fixed rational whose denominator is constant. And this result emerges from a more sophisticated application of these basic techniques of looking for disjoint sets and sunflowers. Now, this would be a natural place to end this video, but as a bonus for all of you who managed to stick it through all this way, I'll just state one other result for fun, which is that besides this, which concerns a problem that's not majority SAT, but something related. Majority SAT is this canonical PP complete problem, but it turns out there is another canonical PP complete problem called greater than majority SAT. In this problem, we're given a CNF and want to decide if its fraction of satisfying assignments is strictly greater than 1/2, as opposed to checking if it's at least 1/2. And just like in the case of majority SAT, for each positive integer k, the complexity of greater than majority SAT restricted to KCNFs, this greater than majority KSAT problem, had been open for quite a while. In our work, we showed that majority KSAT can be solved in polynomial time for every positive integer k. But what about greater than majority KSAT? Well, for the greater than majority 3-SAT problem, it turns out it is possible to solve this problem in polynomial time, just like how majority 3-SAT can be solved in polynomial time. But what about the greater than majority 4-SAT problem? Well, surprisingly, it turns out that greater than majority 4-SAT is actually NP complete. And this seems sort of crazy because this NP completeness, this complexity classification, is so different from the complexity of both greater than majority SAT, which is PP complete, and majority 4-SAT, which is in P. If you want to see an explanation for this bizarre phenomenon, I encourage you to check out the details in our paper. But that's all for this video. Thank you so much for watching it. We appreciate it a lot.